partir desse momento nós estamos gravando, então eu preciso lembrar a todos que se manifestarem durante o seminário que eles estão concordando automaticamente com os termos de uso de imagem e voz. Tá? Boa tarde a todos. Good afternoon, everybody. It's a pleasure to receive for this seminar Professor Rebecca Morrison from University of Colorado, Boulder. Let me introduce Rebecca for those of you who are not familiar with her work and who is she. Rebecca, she has a bachelor degree in physics, and then in her master, she moved to the world of computational and applied mathematics, and she did her master and PhD in the University of Texas, Austin, one of the best universities in the United States. And just after that, she spent some time as a postdoc researcher at Massachusetts Institute of Technology, the famous MIT. After this period, she got a faculty position at the University of Colorado, Boulder in the computer science department. And I think it's good to add when Rebecca and we met for the first time was in 2018 in New York in the WCCM conference, World Conference on Computational Mechanics. We attended the same section, and she presented there, and I started to ask a lot of questions. And after that, we discussed a little bit about a problem regarding epidemic modeling. And in the following day, she attended my talk, and we cooked an idea for a paper there. And after that, by remote meetings, we started to work on this. This was 2018. Previous, before this became the standard for the world, like last year. And fortunately, last year, we were lucky to have our first paper published regarding epidemic modeling, before epidemic modeling was in fashion, okay? And since then, we have been interacting in other activities, like invitation for seminars, and so on. So it's a great pleasure to receive Rebecca here today, and I'm sure you're going to appreciate a lot this talk about learning non-Gaussian graphs. Rebecca, thank you for accepting our invitation, and the show is with you now.
Great. Thank you so much, Americo, for such a nice introduction. It really was such a pleasure to meet him at that conference, and it's kind of what you hope happens at every conference, but that, you know, probably 1 out of 50 you actually meet someone and you know, end up with a paper in a couple years and keep working together. So I've really enjoyed our collaboration. But today I'm going to talk about something different, a sort of other side of my research, still broadly within the world of uncertainty quantification, but different, about learning graphical models. And so this was work that I really got started during that postdoc with Youssef Marzouk at MIT, and Ricardo Baptista, who's finishing up his PhD there now, and also Olivier Zam, who is now at INRIA Grenoble, and he was a postdoc at the same time that I was at MIT. So most of this work was with them. And so I thought I'd start just with a little introduction to the kind of graphs that I want to think about for the next hour. And let me ask right now, do you see my cursor?
No.
No.
Oh, yes, it's moving now.
Around the 7 right now?
Yes,
oh,
yes,
okay.
around the 7.
Okay, so I might use that a little bit, but maybe it's a little hard to see. But okay, so an undirected graphical model is a very simple object. It's just a set of vertices and edges, V and E. And think about these probabilistic graphs where edge has a very particular probabilistic meaning. So a node or a vertex represents a random variable. And in these undirected graphs, the lack of an edge represents conditional independence between two nodes. So I'll say that I and j are not in my edge set, E, if and only if these random variables, xi and xj, are conditionally independent given something, this thing that I call x star here. And there's different formulations for what this x star should be. And here are the sort of 3 common variations. So we can have a pairwise relationship where I can say, this is the weakest of these formulations, that x star will be all of the other variables besides x and j. So in this case, if I can condition on, I'm thinking about these 2 nodes, I and j, if I can condition on everything else, all the other nodes, then I know that these 2 are conditionally independent. Okay. There's also the local property where now this conditioning set we just take to be the neighborhood of one of these nodes. So now I can say, okay, if I want to know if xi is conditionally independent from xj, I look at just say the neighborhood of xi. And if I can condition on those, then I can say that these 2 are independent. And then finally, there's the strongest property of the global. And in this case, all I need is a separator set, which means that if I take my xi and xj, if I find any path, take any path from I to j, if that has to go through some set S, then that set S is a separator set. And so now I can say, if this distribution follows this global Markov property, then these 2 random variables are conditionally independent given any separator set. So that's the most flexible. Okay, it turns out that for the distributions that we care about, ones that are strictly positive, that all of these are actually equivalent. And so for the rest of the talk, you can think about whichever one seems the easiest at the moment. You can use any of these 3. Okay, and just to have a couple concrete examples, this sort of, the classic graph is a chain graph, also called a Markov chain, also called a 1D Ising model. So in this case, we've seen in, Bayesian probability and uncertainty quantification and statistics, and also statements like this that are very common. We think about the probability of some node xt, maybe at the end of this chain, like maybe you think about x8 here. Well, if we want to know the probability of this final node, given all of the ones before it, well, the Markov property says, well, we just need to condition on the one right before it. So maybe if we want to know the probability of x8, given all of the rest of these, well, all we actually have to do is condition on x7. So these are very common Markov models. We can also write that in this format here, where we say xt is conditionally independent from xj, given just this xt minus 1. Okay, so there's one common example. Here's another one called a grid graph or a 2D Ising model. So here it's common to think about, let's say I want to know the conditional independence between this fit node 5 and something else. Well, I can say 5 is conditionally independent from any of these blue nodes once I take the neighborhood of 5. So you can see this is these nodes 2, 3, 8, and 9 are the neighborhood of 5. They're also a separator set between 5 and anything else. If you take a path from any blue node to 5, you have to go through those green nodes. So that's a separator set also. Okay. Another classic example is the star graph. Usually also called a naive Bayes model in some cases. It's more common to see it as a directed graph in that case, but it's similar. So here I can say, for example, that any of these nodes on the outside of my star, like 4 and 5 up at the top, those are going to be conditionally independent once I condition on the central node. So this is often in classification algorithms, we think of the central node as some kind of label. And if I can condition on my label, then my predictions of what that label is are independent. Okay, so those are some examples. These are the kind of graphs we're thinking about. If we have that structure, then it's really useful for all different sorts of applications and machine learning and handwriting recognition and speech classification tasks, and it comes up in genetics, and there's sort of limitless applications. And in a lot of cases, you may know what that graph should look like. You say, I know a priori that my data is structured in this way. And if you know that, it's great, because then having this graphical structure means that tasks, other uncertainty quantification tasks that we want to do, like inference and prediction, can become much easier and faster. Because we always have to condition, and if we can simplify what that conditioning is, then if we can condition on a chain, then everything is a lot faster than having to condition on everything all at once. So it's, we want to know what these graphs are. And in some cases, we may know from scientific expertise, or just because we've developed the problem to be that way, or because of very strong assumptions, we know what the graph is. This project was about, well, what if we have the data, but we don't know the graph? So we want to take the data and we want to find the graph. Okay, so before I really get into that, there's just a little bit of notation that should be consistent throughout this whole talk. So if I use this variable eta, that's a standard normal in D dimensions. We'll use rho to mean just some Gaussian, not necessarily, still with zero mean, basically without loss of generality, but it can have a non-trivial covariance. And pi will be some non-Gaussian, what we'll call target distribution. We'll assume it's zero mean and positive, strictly positive. Okay, so eta, standard normal, rho, Gaussian, pi, something non-Gaussian. We don't know what it is. Okay, so to start, a really nice problem is to say, what if we know our data is Gaussian? What is its graph? Okay, so we have data from rho. And so let's think about the distribution of rho. It's proportional to this exponential term with x transpose times the inverse covariance times x. Okay, and it turns out in the Gaussian case, this has been known for a long, long time, that there is an edge, ij, so there is an edge between variables I and j, if and only if the ijth entry of the inverse covariance or precision, that's the same thing. So if and only if this ijth entry of the precision is non-zero. So when you look at this up here, you think about sort of multiplying this vector times this matrix times this vector, you need something that sort of connects I and j up here, sort of keeps them together, and that's going to be when this thing is non-zero. Otherwise, what happens is this distribution, you can separate it into what are called factors, and if things are in different factors, then they're conditionally independent. But anyway, the point is, in this case, it's relatively easy to...
So,
go ahead.
May I ask a question?
Yeah.
So if you have a set of independent random variables, their graphs will be disconnected. So
Just
they will connect only with themselves. Or you will
right.
only have a self loop.
Yeah, we won't, right. So exactly, if you have a bunch of independent variables, then this, say,
I'm
Gaussian.
thinking the limit case, an identity. So in an identity covariance, each variable is only connected with itself.
Right.
Okay. So this graph structure is a graphical way to represent the correlation structure among the random variables.
Yes and no. So the covariance, if you take away this inverse, what does the covariance tell you? The covariance matrix itself tells you exactly about independence in a Gaussian. Okay, let me back up. This is a great question. So for a general distribution, a covariance matrix doesn't tell you about independence at all. It just tells you about correlation.
Mm-hmm.
Now, if your distribution is Gaussian, then you get this extra nice property that if you have a 0 in the covariance matrix, you do know that those two variables are marginally independent.
Mm-hmm.
So a Gaussian is really nice because the covariance does tell you about marginal independence.
Okay, so that graphical structure,
but now
it translates the independence relation, not the correlation among the random variables. Correct?
That's right.
I misunderstood in the beginning. So
and not just and these graphs are not telling you the structure of the correlation, or they're telling you about conditional or they're not. An undirected graphical model does not tell you directly about marginal independence. It tells you about conditional independence. So you can think for a Gaussian, you should think a covariance tells you about marginal independence, and an inverse covariance tells you about conditional independence.
Mm-hmm. Okay.
Right. So in the non-Gaussian case, the covariance and the inverse covariance don't tell you anything about independence. They just tell you about correlations, and the inverse covariance is sometimes called like a partial correlation or something else. But what's so nice about a Gaussian is that zero correlation implies marginal independence, and 0 in the inverse covariance implies conditional independence.
Mm-hmm.
That's not true in general for other distributions. Okay. Good. Thank you.
You're welcome.
Okay. So so this is good. This is right at the heart of everything. Okay. But now we make one more observation. And that's that I'm going to take my Gaussian rho. It's a function of x, right? This thing is a function of x up here. I'm going to take the log of this density. And now I'm going to take the mixed partial derivative. And what do I get? Well, I just get up to a negative sign. I get this entry here of the inverse covariance. I get the ijth entry of the inverse covariance. Now for a Gaussian, the x's drop out, and this is constant with x. So for a Gaussian, I can say this relationship on the left is what we've already seen. There is an edge if and only if the ijth entry of this precision is not equal to 0. Now I can also say that's if and only if this mixed partial derivative of the log density is not equal to 0. Because these two things are equivalent. Okay, so we're going to use this. Now we're going to try to go to non-Gaussian data. So let's think about, sorry, let me go back to the Gaussian graph. Let's say we want to learn the graph, the undirected graph of Gaussian data. What do? Well, we can estimate, so we have samples. Say we have enough samples. We can estimate the covariance matrix. We can just compute it. We can take its inverse. And we can see we have a thresholding problem because entries won't be numerically zero, but we can see which entries are really close to zero, and we threshold it somewhere, and that gives us the graph, right? So in the Gaussian case, it's relatively easy to identify the graph. Now, people have done a lot of nice work on what happens when you don't have a lot of samples, which then becomes a harder problem. But the way to identify the graph is fairly straightforward in the Gaussian world. Okay, so now let's say we have data that's non-Gaussian. Now what do? So we can still compute the inverse covariance, but the problem is that doesn't necessarily tell us anything about conditional independence. So once your data is non-Gaussian, then this correspondence between your inverse covariance matrix, your precision matrix, and your graph is cut. I mean, that relationship doesn't hold. So in the same way that, think about a banana distribution, you can have in 2 dimensions. For a banana distribution, you have 2 variables that may be uncorrelated. So there's a 0 in your covariance, but those things are not marginally independent, right? So the same thing can happen here. You can have zeros in your inverse covariance, but it doesn't mean anything for the graph. Okay, so we have to do something else. But it turns out that we can still use this other relationship. So I've written it the other way around and say there's no edge between variables I and j if and only if this mixed partial derivative of this log density of pi, now pi is some non-Gaussian thing, if this mixed partial derivative is 0 for all x, so it might not be constant anymore. If this thing is 0 for all x, then we can say there's no edge. So
Rebecca,
that still holds. Yeah.
This is valid only for 0, no edge. So the mixed partial derivative is 0. But if the mixed partial derivative is different from 0, you can say that there is an edge even in this general case.
Yes.
Okay. So you lose the correspondence with the inverse covariance, but you keep the correspondence with the mixed partial derivatives of the log density.
Exactly.
May I ask, extrapolate the ideas? Isn't it possible, in the general case, you try to use a isoprobabilistic transform to put your variables Gaussian, try to infer there, and then be back?
Yeah, so that's a really good question. So let me come, maybe we'll return to that question.
Okay, we can discuss this later.
Yeah.
Just an idea I have during the presentation here.
Yeah. So we'll talk about something similar at the end, and then we can come back and think about that question, I think. But yeah, that's a good question. Okay. So we want to use this result to find out what the graph should be. Okay, so I'm gonna give this thing a name. So I'm gonna take, so we have to do this from samples. We have to do this numerically. So I'm gonna take an expectation of this mixed partial derivative. We're gonna square it for a couple reasons. One is so that things don't cancel out. Also because this then relates very nicely to, excuse me, conditional and mutual information. And now I'll take an expectation with respect to the samples that I have. So this then, now I have a matrix. So I have one of these estimates for every pair of variables. So I'm going to think of this as a matrix, a symmetric matrix omega. So this omega is really like a score matrix of conditional independence, where if something is, if omega ij is large, then we can easily say, okay, there should be an edge there. If it's very small, then again, we have a thresholding problem because this is all numerical, but then if this is very small, then we may be able to threshold it and say, we don't need an edge between I and j, or there shouldn't be an edge. Okay, what's the problem with doing this now? We need some expression for pi because we need to be able to compute this mixed partial derivative of log density. So how do we do that if we just have samples? Okay, so so we've traded one problem for another. Now we have a density estimation problem because we have to express pi somehow. Okay, I'm gonna ignore that problem for a second and just sort of put together what we've seen so far. So this is an initial version of this algorithm. We'll call it the non-iterative sparsity identification of non-Gaussian distributions, or NSIG. And these are the main components. The first thing we have to do is we can't get around this density estimate. Well, there's ongoing work now to try to do this in a smarter way, but I'll talk about that at the end maybe a little bit. But we're gonna...
Sorry to interrupt you. If I may have a question.
Sure.
As far as you constructing this idea and you connect that to some examples, including a simple Markov chain, but is it like something the algorithm you're proposing or looking at, can I use that to say to unravel some hidden states on a Markov chain or construct a Markov chain from dynamic data, from some data, and using this approach or some similar things connected to that? Or is it something that you're aiming at, or is it possible to do?
Yeah. So right now this approach relies on, yeah, that's a good question. Right now this algorithm relies on the fact that you have data from every node. So something like a hidden Markov model would not immediately work here because what you have to tell the algorithm basically, this is the data I have in d dimensions. It will find a d-dimensional graph. It won't find hidden nodes.
I see that. I see.
Yeah.
Thank you. Yeah.
Yeah, but whether or not we could use this to say, I think something is missing.
Yeah, this is what I had in mind actually. But I mean,
yeah.
sorry. So, yeah.
I have to think more about that.
Thank you very much.
Yeah.
Yeah,
But good question. Yeah. Okay. Good. I mean, in an ad hoc way, you may get a graph, you may find a graph and think to yourself, this graph really doesn't make sense. I think if I condition on something else, I should see a sparser graph. Then, there may be something like that you could use this for, but it would be sort of you would need some kind of expert knowledge to help you. Okay, so let's say, so we're gonna do this. I better pick up my pace a little bit. Or I might cut in since we're doing questions in between, but cut into that 50 minutes. Okay, so we're gonna use an object called a transport map to build a density estimate of pi. Once we have pi, then we can compute an estimate of this score matrix omega. We'll call it omega hat. Then we have to threshold omega hat. How to threshold omega hat is a very interesting problem, and I'm also going to ignore it like completely during this talk, but we have a paper on arXiv out and submitted that talks a lot about this if you are interested, and I can point you there, we can talk more about it. Okay, now once I threshold omega hat, now I've found my graph. So that's it. This is not that complicated of an algorithm. And so now I'll say just a couple words about transport maps. This is more than you need to know for this talk, but there's just one piece of it that's important. So I just want to get to this one piece. Okay, so what does a transport map do? A transport map couples deterministically two probability measures. So remember, we said eta is all standard normal, and pi is, say, some unknown thing. I call this S sharp pi. This is the push forward of pi under this map S. I can also talk about the pullback. So it's just a coupling. It's just a map. It's a map. This is a transport map. A map between these two measures, pi and eta. Okay, how do we do that? Actually compute these things. Well, we take, this is going from a d-dimensional thing to another d-dimensional thing. This map has d dimensions in it. For the kth, we have to take each component and parameterize it. And so there's a couple nice things about the particular parameterization we're going to use. It's monotone and lower triangular. Lower triangular means that the kth component of this map only depends on variables 1 through k. We can do that without it, just completely in general, without any loss of generality. And then we're going to have a function, a Hermite function here for variables 1 through k minus 1. Then we're going to have this integrated form. What G is just another function to ensure numerical stability. HK is another Hermite function. And this thing is integrated with this dummy variable t up until zk. So this integration ensures that this whole thing is monotone in the kth variable. Why is that good? That's good because we can take an inverse of this function. If we know it's monotone, then we can take an inverse, right? And still get a function. Okay, all of these details for this talk don't matter. The only thing that is important right now is that these Hermite functions, or think of Hermite polynomials, they have some coefficients. We're going to lump all of those coefficients into this vector alpha. And really the only takeaway here is that we have control over how we parameterize these maps. And the choice, the sort of clear choice, is what polynomial order these functions ck and hk should be. So that's important. So beta is this polynomial order. If beta is small, these maps are more restricted, where they can't do as much, and we're always going to map back and forth to a standard normal. If beta is really high, then you have a lot of flexibility in what kind of maps you can do, and you can map to all sorts of weird looking different distributions. Okay, so beta controls sort of how rich this map representation is. But if the higher beta is, the more parameters you have, right? And that we're going to have to optimize for these parameters. So, you know, and we have finite number of samples. So we want to keep beta as low as we can and still try to capture this map representation.
Just a little bit obvious question. User meet because it's the orthogonal family of polynomials for the Gaussian, correct?
Yeah, that's that's, you know, I think you could use others here, but
perhaps
for the Gaussian case, I think you get I want to check my numerics. I haven't thought about that in a long time.
I think Hermite is the optimal for the Gaussian.
It is
you
optimal.
Use others, but you need to identify more coefficients.
In the definitely for like a PCE type expansion, that's optimal, and I think that carries over here. But I have to check before I say with total certainty, because this isn't quite the same as like a polynomial chaos expansion where you have that. It's not that kind of correspondence, but yeah, I should check that.
Okay.
Actually. Okay. I'll get back to you, America, on that. Okay. So, but in any rate, we have this vector of coefficients alpha, and we can optimize for them. And this is just, again, this is sort of more detail than you need to see, but this is just to show you that I can minimize the Kullback-Leibler divergence between pi, this unknown distribution, and this pullback of eta according to this map that's parametrized by alpha. And so the great thing about, if I write this out, that's equivalent to this second line. That's just this expectation over the minimizer. I don't have to worry about this piece that comes from pi. If you think about writing out your KL and getting two terms, you just need this piece. And now I can compute that if I have sample z from pi. So this is great. This is just saying I can do this. I can find a nice maximum likelihood estimate for my parameters alpha given samples from my unknown distribution pi. Okay. Okay, the simplest example is when we have a linear map. So in this case, beta is equal to 1. Everything is linear. So if you think about some samples x that are sampled from some normal rho with covariance sigma, we can take the Cholesky decomposition of that as KK transpose. Okay, what do we all know? We've probably all used this. If we take K inverse and apply it to X, these samples, what do I get? I get something that's distributed like a standard normal, right? So, you know, going the other way around, if I apply K, if I take this matrix K and I apply it to samples from a standard normal, what will it give me? It'll give me samples from rho, right? So K and K inverse are transport maps that map between rho and eta. So we can write that again here. We can think of S, this map S, as a function of these samples X. It's like applying K inverse. So I start with something from rho and I get something in eta. So I can write that as, in this transport map notation, as just S sharp rho equals eta. Okay, so that's when I have a linear map, beta is equal to 1. Now this is the same process, but I can let beta be bigger than 1, and that's what allows me to describe non-linear, non-Gaussian distributions. So there's a whole slew of code that transportmaps.mit.edu that members of that group have been working on, and a lot of resources there, open source code, if you want to look at that too. Okay, this is already what we've seen. I'm going to skip it. Okay, and I'm really running out of time. So there's more in this problem that we can take advantage of. And I'll just go through this really quickly because I want to get to some of the examples that we've done. But also turns out that there's another notion of sparsity. And what do we want to do? We usually want to find sparse graphs if we can, if it exists. And it turns out there's this connection between what we call the sparsity of the graph, the standard sparsity, the lack of edges in the graph, and what we call the sparsity of the map, of the transport map. So remember before I said, if you look at this map down on the bottom, you know, we know this third component, say, only needs to depend on the first 3 random variables. That's true, but it turns out that in some cases you may not even need all of those variables. So in this case, you have to know what the graph is first. So let's think about this graph in this figure A here. So I have a graph with some sparsity. You know, there are a lot of missing edges in this graph, and I have a good ordering. Then it turns out that when I make the map S that I need to describe any distribution that satisfies the conditional independence properties of this graph, any distribution that satisfies those, I can leave out more variables in the parameterization of my map. So for example, this 5th component for S5, I don't even need these variables x1, x2, and x3. I just need 4 and 5. Why? Well, because 5 is connected to 4, approximately. I mean, it is connected to 4, but so what do we want to do? Now we say, okay, or why do we care? Well, we care because if we can leave out these variables, like in the 4th and 5th components here of this map, if we can leave those out, what does that mean? It means we have fewer parameters in this whole map thing. And with finite number of samples, the fewer parameters we have, the better, right? So if we have fewer parameters, we get a better estimate of that alpha, of those coefficients alpha. We get a better density estimate, and then we get a better estimate of omega, our score of conditional independence. So the idea is we want to use this. We have to find an initial graph first. Once we find an initial one, we want to use it. So what are we going to do? We're going to identify the graph that using this algorithm that we've already seen. Now we hopefully have some sparsity in that graph. We have to get a good ordering. That's another problem. But we can use heuristics, and it's an NP hard problem, but we can use heuristics and it's okay. So we get our sparse graph, a good ordering. That means fewer map parameters. Fewer map parameters mean better estimates. Okay, now we actually we remove those variables from our map, define a new space of maps that don't have those parameters in them anymore. We rerun this little piece of the algorithm and sing, and potentially identify a new graph because we have these better estimates. So we kind of want to get tighter as we keep going, and so on. We'll terminate when the number of edges is no longer decreasing. Okay, I'm going to skip this slide too. Okay, so let's just see a couple quick examples. So let's think about, we call this the butterfly distribution because this two-dimensional marginal looks like a butterfly. We have pairs of random variables, pi and qi. Pi is standard normal, and qi is pi times wi, and w is another standard normal. So if you look at this data, if you just look at the one-dimensional marginals, so this is for one pair, it really looks, it doesn't look that far from Gaussian. So you might look at this data and say, well, I think we can do a Gaussian approximation and be fine. So what happens? This is what the graph looks like, graphically with the nodes and edges. This is a matrix representation where, the diagonal is filled in, and then we have these little blocks for the off diagonal. Okay, so we want to recover that. So when we did this example, first we have this ordering problem, so we permuted the order because we wanted to make sure the algorithm could sort itself out. And then we run sting. In this case, we used beta equals 3. And just after the first iteration, this is what we got. It's pretty close, but we have this one extra edge. Then we run it again. It looks good. Then we run it again. We want to make sure it doesn't keep changing. We get the same thing. We terminate. We got the correct graph. Everybody's happy. So we said, okay, well, what happened if we assumed, basically, if we did this Gaussian approximation to this data, assume it's Gaussian, what happens? In this case, it misses all of the edges. So because this thing is kind of symmetric in a way, if you think about that 2D marginal, it's sort of symmetric. This Gaussian approximation does not do a good job here. It misses all the edges. If you run this, it would tell you, if you assume this data is Gaussian, you would get the answer that all of these variables are actually independent and there's no edges anywhere at all. Okay, so that's not good. Another example I've worked on is comes more from like physics-based modeling and thinking about how to decouple these really big computational physics-based models. And so in particular, this was a fire detection satellite model. And so we want to know if we can sort of remove some of the feedback and some of these arrows that, so okay, what's going on? We have 3 disciplines: orbit, power, and attitude. And then we have 3 quantities of interest: total torque, total power, and the area of the solar array. So there are these 3 disciplines, and there's coupling variables that are listed here that move back and forth between these disciplines. So Ricardo had actually worked on how to, if it was possible to decouple this at all by taking the model output distributions of these quantities of interest from the fully coupled model and then these candidate, like partially or fully decoupled models, and just to see in the KL divergence how different were the quantity of interest distributions, how different were those from the fully coupled model and these decoupled models. And he actually found in this problem, you could decouple everything, like you basically ignore orbit. You could decouple everything. Well, you still need these inputs here, but they don't, well, anyway, you can just set them. Then, and you get, you could decouple everything and you would still get a good answer. And we actually took this data on the coupling variables and the quantities of interest, and we found the same thing, that the graph actually split itself into these different disciplines. So that was really cool. We still have to write this up actually, but I think it's a really neat sort of physics-based application for these like graphical models that's more unusual in that world. Okay, and then the last example I have, and I'm almost done, is a classic non-Gaussian test case for these learning algorithms that are called non-paranormal. It's really a Gaussian copula. Okay, so there's a lot on this slide. What is going on? So we have, our data is this X, and if we apply this, what's called a diagonal transformation to each of these variables, x1 through xd, we get something back that's multivariate normal. So what in map notation, what we can say, so this is multivariate normal, not just a standard normal. So what is pi here, this distribution of interest? Well, if you see my cursor, I'm starting on this eta here. We start with eta. Think about applying a linear map L to eta. That gives us some multivariate normal. That's what I'm talking about up here. That gives us a multivariate normal. Then we apply this F sharp, it's actually a pullback. And F sharp is this diagonal thing here, and that describes pi. Okay, the reason these are common test cases are because since this piece here, or this piece here, is multivariate normal, right off the bat, we know what, if we know what that multivariate normal is, we know what the graph is, because it's the inverse covariance again. And what's also known is that if you apply these diagonal transformations here, you get the same graph. So that's good, because you may have data. So this is a marginal from one of these problems. This is apparently extremely non-Gaussian, right? But it's a good test case because we know we know what the graph is. Okay, and I'm just putting this up here. This is how you would actually sample from this distribution. This is just to show you that this really is like, it's a totally crazy looking thing. It's really not Gaussian. Okay, so what happens is in this example. So let's say we do a 10-dimensional case. Here's our true graph. This is what we should recover. We took this data, we ran it through the algorithm just with beta equals 2, and we got the correct graph. Everyone, that seems great. We're happy. We thought, well, you know, kind of like the butterfly case, what would happen if we use beta equals 1? Like it's probably going to be really bad, right? Because this thing looks really non-Gaussian. So we'll say, okay, just to check, let's see like how bad this thing really is with beta equals 1. We did it and we still got the correct graph. So this was a total shock. Like, why in the world would we get the correct graph? Assuming, this is like assuming you see this data and you say, yeah, but I can assume that that's Gaussian. Okay, so totally non-Gaussian looking data, but we use a linear map, we still get the correct graph. Okay, so we looked at the inverse covariance. You know, we can compute it from the data. And that inverse covariance is still revealing the graph. So you can see like these yellow things are 0-ish, close to 0. And these green ones that are, you know, significantly non-zero are exactly where the edges are. So this whole time I've been telling you for non-Gaussian data, the inverse covariance doesn't tell you the graph. Well, apparently in this case it does. This was a big mystery. Why should this work? And right now, this is what I've been working on for the past year. And we just put up a paper on Archive that explains this phenomenon for these, in particular for these diagonal transformations. So it turns out it's actually not a very good test case for Gaussian, for non-Gaussian data, because, well, when you apply these diagonal transformations, things still sort of behave like Gaussians. Even though those marginals, you can have horrible looking marginals, they, in terms of the graph, in terms of the graph, they still, and the covariance, they still really behave like Gaussians. So anyway, we just put this paper up. I'd love to talk about it more, but I'm obviously running out of time. So let me skip this. We can come back to it. Well, so the idea is, yeah, if you apply these diagonal transformations, it doesn't matter in a way if this is really nonlinear. You sort of need the beta, you need the right beta to capture this part before you apply this diagonal part D here. So the same thing happened. So here L is linear. So in that previous example, we just needed beta equals 1. We've seen the same thing. If say you have M here, say M, we call it base class beta equals 2. Say this is described with polynomial order 2. Even if you use some crazy diagonal thing here that's super nonlinear and horrible, you'd need beta equals 50, who knows what, to get the right graph. You just need the beta of this first part. You need this 2. Okay, so we call this problem the information gap. Okay, so there's kind of this sort of interesting issue now. We can discover a non-Gaussian graph, but what beta to choose is a big problem. So in some cases, like the butterfly, if we incorrectly assume that data is Gaussian, it was complete failure. But in other cases, like this non-paranormal one, even though that one looks really non-Gaussian, it actually is totally fine to use a linear map and assume that the data is Gaussian. It's no problem. And the good thing about that is that then you can do things really fast. It doesn't take as much time, and it's easy to get nice estimates. Okay, so we're looking at a bunch of other stuff. Further analysis of this information gap. We have a pretty good handle in that paper that I just mentioned on what is happening in that linear case, but we do not have it, for that second type where like if you have that M, where M is base class beta equals 2, we don't have theory to explain that. We've been looking at time varying graphs, heterogeneous data, like consistency and sample efficiency problems, and now in particular trying to move to higher dimensional problems by avoiding this, some of the heavy computations that go into the algorithm that I presented here, and with what's called a neighborhood selection approach, where instead of trying to, right now everything's kind of done like globally at each step of the algorithm, but we're looking at how to build up the graph kind of node by node. Okay, so I'll end there, and thank you so much. And I have more time, but I know we're over time. Probably some people have had to go, but I can stay and we can have more discussion now too. So thanks.
Thank you, Rebecca. We're open for questions now. Those who want to ask a question, please raise your hands. I have more questions.
Okay.
Could
And I
you
have a
return to the
better, we can talk more about your earlier question too of the Gaussian approximation, because since we saw some examples too. But anyway, go ahead.
I have a question about the second example. That one you could split the contributions of the different physical domains, the
Yeah.
physical problems. And try to explore this a little bit more. Suppose you have a simulator, a multi-physics simulator with different physical domains, very complex fluid structure interaction, for instance, or control in turbulence. Is it always possible to impose a sparse structure that split the different contributions in that beautiful way you showed? No. What is the main ingredient that allow you to do this in some situations, and I believe not in others?
Right. So So in some cases, so I think it'll be problem dependent. In this example we had this very clean result where everything just actually split into just completely decoupled. But you could imagine, so for example, in this fully coupled model, you have output from attitude going to power, and you have output from power going to attitude. So, you know, you could imagine, you might identify a graph that removes some of these edges, or, you know, maybe it removes this edge between I max and this total torque, but it doesn't remove this other edge, and you still need to have that coupling. So I agree, there's not an easy correspondence between removing an edge and saying, oh, automatically that means that there's some decoupling that can happen. And I actually don't think that's true. So you might find that you don't need a little bit of that communication between one to the next, but you still need some. Now, whether that, if you still have to communicate from one discipline to another, you know, it may not save you anything if you still have to pass 5 variables instead of 10, maybe you should just pass all 10 if you have to do it anyway. Mm-hmm. So, you know, there's also, yeah, so I think that, you know, we're thinking about these details here, but yeah, I don't have a super clean answer, because
it's a complex question.
It would be problem dependent. It also depends on, you know, what the you know, potentially what the quantities of interest are. So, and where they come from. But, you know, this is super new. This type of application, I'd say I haven't really seen anything else like it. So I think there's a lot to try to still nail down here. But definitely the sort of the easiest thing is if you see a graph that tells you, you know, this component, I don't actually need it. Like if I can fully remove that from the prediction for this quantity of interest, if I completely decouple some component, you know, then then it's more clear cut, right? And that's kind of that is what we saw in this example.
Mm-hmm. I was thinking in a possible application in interaction between epidemics and economics. Some people are trying to understand the effects. And if you could split this in a very clear fashion, in a very clear pattern, could be very good.
Hmm.
We have other questions here. Zushil raised her hand. Please, Zushil, you can ask your question.
Oh, thank you. Thank you, Rebecca, very much for your talk. I really, well, it's not, let's try to formalize a question. Before that, I want to think this work that you presented is in archive in that address that link that you give in your talk.
Yeah.
Yes.
So there's two main papers right now that are both on archive. The link that I showed here, this is only about this kind of example.
Oh yes, it's the example I want to ask you.
Okay.
Could you go to the first slide where you have the distribution?
Yeah.
Well, density. There we just have an application for epidemics for stochastic compartmental models, and we applied in a specific case, and we have exactly a distribution in the like this you have there, and so the very cost of this application is to compute the transition matrix, you know, because we make the original graphs, the matrix, you know, with the position, with the values given by some similar to graphic, and
Right.
And we obtained the transition matrix. That's the final and the final study we have needs a very expensive computational cost in multiplying this matrix, and finally we have that distribution. My question is, do you know some application, or you imagine an application for having some kind of density in distribution in a way that you explain, which could allow not to computing those matrix multiplications for going to the final result?
I don't know off the top of my head. No. So when you say that you have a distribution that looks like this one, do you mean you have something where if you apply?
Yes, I compute at the beginning a transition matrix, and that's the information I have for my distribution. And so for having the final result of the evolution of that epidemics, I need to make multiplication that simulates the evolution of that epidemics in terms of this transition matrix. So it's very computational cost, highly computational cost, and so I was interested in some maybe another formalism that could make for us don't need to calculate to compute those. Yes, to have to reach a final result like this. I don't know. I will. That's why I will see your papers if I could understand what is performed and if it has some application in that specific work.
Yeah. So The other paper, and I can share a link at least with Americo after the talk for the original paper does have an example from a dynamic system, like a Lorentz 96 model, where we identify the graph from steady state, the data from the steady state of this chaotic system. And so that might be the most relevant application, but I'm not sure. I'm not. It's hard to say. Maybe you can send me another paper with the problem formulation, or I'll show you this other example in the other paper that I don't have here, and to connect the two, because these graphs are not. And this might already be clear, but the graphs that we have here are, they're not the same as these transition graphs. So.
Oh no, yes,
Yeah,
it's
okay.
not the transition, no.
Like it's right, but so I don't know if finding the graph would help you in that problem, but maybe. So, or maybe you could simplify. I don't know.
Okay. No, okay, thank you. I will.
But I'll share that. The other example maybe is the most relevant, but I'll share the archive link with Americo.
Okay, we have another person who wished to ask a question, Professor Guilherme. Guilherme, please.
Okay. Hi, Rebecca. Thank you very much for your interesting talk. I want to ask you a question about the limitations of such a model, because perhaps in a counter case, you have a counter example. You tried to model the graph. The data tells you that the graph is okay, but when you look to other data, you see that the model doesn't fit very well. Do you have any counter example like that in your experience with the models you tried, with the systems you tried to model? Because sometimes I have that problem. I work a lot with machine learning, and sometimes you try to fit a model for image classification, that's my field, and then you see that the model you had tried to simulate is not fitting very well to other kind of data, new data. Doesn't use it during training.
So, that's really a very good idea to sort of, we haven't, I'm trying to think of all the examples we've run right now. I don't think we've run across that problem in a sense, but it's probably because we should do more testing. And in the examples we've run, we sort of take all the data we can get and find the graph, and then say, okay, this is the best thing we can do for this problem. But I completely understand. I agree with your point that in a lot of cases you're going to try to find the graph and then you want to use it. So we've kind of, and that once you use it, you might have more problems, and you might realize something is wrong. I would say this work is maybe still preliminary. I mean, it's still, we've kind of just been doing the first part of that problem of like, how do you even find the graph in the first place? But you know, we should be thinking about, okay, what if we find this graph, then let's use it. That'll probably bring up these problems that you're mentioning, but we've kind of stopped at that first part.
Okay, thank you very much.
Yeah, but yeah, no, I'm sure that would come up if we told some application group, hey, you should use this graph. I could certainly see that they might say, well, you know, your model doesn't.
There are some applications that you don't have enough data, for example.
Right.
Or for example, also the model should be too complex.
Right.
And then you come into another questions that will make your research advance, of course.
Right. Right. So, for these graph learning problems, also it's tricky to find good test cases, because if the data is not Gaussian and it's not generated yourself, if you don't generate it yourself and it's non-Gaussian, then you're working with real data and nobody knows what the graph is. So then we have the problem of, you know, you can report a graph, but there's no guarantee that it's the right one, and then you run into the sample size problem. So I mean, so we did look, we looked at, you know, this is used in genetics, and we looked at a gene data set, and we tried to do an example, but you know, there was very little data, and there was really no sort of, no one knew what the graph really was. So, you know, you can do it, but you can run this algorithm, it will give you a graph, but there's no guarantee that you're getting the right graph. So in that case, like, we haven't even reported those results. We abandoned that test case because, you know, we just couldn't say anything. The uncertainty was too big in that case.
And how you can, for example, look at a graph about some simulation you did and see, oh, it doesn't make sense, or you can recognize that.
Well, yeah. So
do you have any methods in mind about how can I recognize if I got a difficult example enough for my model doesn't fit very well?
Yeah, I don't know. I think it does depend on just that sort of expert knowledge of how much you already know about that problem. You know, otherwise, there's no reason to say anything about the graph that you find. So you really have to know something. It's kind of like having a prior on what you think the graph should be. If you find something that's very, very different from your prior, then you might not believe it. So, you know, it'd be an interesting way to pose this. We could pose a prior on the graph and then update it with this, you know, this likelihood approach. I mean, this as a likelihood sort of, and then take our prior beliefs into account. We haven't done that, but it's an interesting idea. But you know, we're thinking about this a little bit more also in this realm of dynamical systems. So, you know, I should include it in the next time I give this talk, but you know, there's actually not a well understood correspondence between, say, steady state data from a dynamical system and what the graph should be. So so we did an example where we found the graph, but there's no sort of mathematical proof that says, you know, oh, you have this set of ODEs that generates this data, and now you take data from the system. What does the graph actually look like? That correspondence doesn't actually exist, as far as I know. If someone knows about that, I would love to hear it, but I don't think it does. So in that case, when we ran this Lorentz problem, you know, in the Lorentz problem, you're connected to your neighbors. You're connected to your neighbors in the right-hand side of the differential equation. Now, does that mean that the graph should be that you're connected to your neighbors? You know, maybe. So we kind of looked at this problem, and we actually included it in one of these papers. And so that one, we kind of went off some intuition. You know, we think that in that case, we actually think that the graph is dense, because kind of everything gets propagated through everything else through these coupled differential equations. We actually think the graph is dense in that case, but we can say, what are like the strongest edges? We think it should kind of follow the form of those differential equations, but it's not, you know, that's not there's no formal statement to connect those two right now. So that's something I'm very interested in sort of formalizing as well. But so in that case, we were just going off of like, we kind of think this is what it should be, but we don't know.
Thank you very much.
Thank you.
Okay.
It was really, really great questions. So thanks. Yeah.
Other questions? So if no, I wish to acknowledge Rebecca again for this very nice talk, for accepting our invitation. And I acknowledge all of you who stayed until the end of the talk. Okay. So Rebecca, it was a pleasure to receive you here. And if you have time, maybe we can continue that discussion for a few minutes after I stop the recording.
Sure. I'm going to stop sharing actually, and then I can see you again.